Fernando, for the introduction. Okay, so, and it's a pleasure for me to be here. This is my second time, actually, in the, here. The first time was, I think it was 2013, so it was 10 years ago. But what I'm going to talk is actually kind of related to what I talked 10 years ago here. So, and you will see why the title is a bit funny. So let me see. It doesn't catch there. Maybe I should come here. Okay. So this is a work that I've been doing for a long time. Actually started 10 years ago with Chico Alcaraz, and then who is in San Carlos, and then we had some works with Sona Najafi, who is now in IBM Boston. Still we are working on some stuff. And then I have another colleague of mine, which is a professor in Universidade, another one, Rajabpour in Shiraz University, and then a postdoc in Augsburg University, Rényi, and then a master's student that I have. Okay, but what I'm going to talk today, this is really a process the last 10 years, but what I'm going to talk today is based on work that with Mortaza Najafi and Abu Faz Rajabpour, we kind of finished. We have the draft, but we're just taking a lot of time to edit it. Okay, so what I'm going to talk is kind of so simple that I can even tell it to the high school student. So what is it? So take a matrix, a square matrix, n by n, and then the submatrix can be defined by taking a bunch of rows and columns, right? So this is the submatrix. Now, if you take I and j the same rows and the same columns, then I can define AI. So here is the I and j are the same. And then just take the determinant of this guy. I think you know from your high school that that's called minor, principal minor of the matrix, right? And then what I'm interested is actually the sum of power alpha of these principal minors. Okay? So if you have a matrix of n by n, the number of principal minors that we have is just a simple combinatorics is going to be 2 power n. Okay, so I would like to see how I can calculate this. Okay, then you may say that, well, is there anything interesting there? Well, the point is, so sorry, it's jumping ahead. Okay. Okay, so when alpha is bigger than 1, it's proven that the problem is NP-hard. Well, such a simple problem is actually a bit hopeless, apparently. So this is shown in different levels for different alphas and stuff by a bunch of people that they do this complexity theory kind of stuff, okay? For alpha equal 1, it's actually a very simple thing. You can show that the sum of principal minors are going to be just the determinant of identity plus the matrix. So it's a polynomial problem, okay? Well, for the first time last May, when I wanted to present this talk, then I ended up watching this great satirical comedy. I don't know, anybody is actually recognizing this? Do we have anybody who knows about this character and the movie? Well, okay, so this is a portrait of this guy, Ripper, General Ripper, a crazy guy, in the movie called Dr. Strangelove, or How He Stopped Worrying and Loved the Bump. Okay, so in last May, where we were all worried about it, we're still worrying about it, but okay, so I found it kind of fitting for the current atmosphere of the world. Anyway, so, and these are just a bunch of jokes that, you know, the movie is a comedy. Anyway, so, so why, well, in this talk, I will try to tell you why I got interested to this problem, okay, so some motivations. And then I will try to give you a Grassmann integral representation for this problem, which is a mathematical statement. And then how to really calculate these things, some sort of analytical calculation of the things, and how this can be useful to calculate something in transfer field Ising chain, which I guess most of you know what it is, okay? And then conclusions. Okay, so what is the first motivation, which was my main reason to start studying this problem, was coming from a Rényi entropy of quantum many-body systems. So what do I mean with Rényi entropy? First of all, just don't confuse this Rényi entropy with the quantum Rényi entropy that all of you kind of know about it. So this is just, you know, I take a normalized ground state of a quantum chain Hamiltonian, and then I write this in a particular local basis, right? And then, well, so if you are familiar with the spin chain, it's just like you take the sigma z or sigma x, right? You have a crazy ground state or whatever, and then you just take the probability of each of these configurations, and then you just calculate this guy. So basically, this is just the diagonal elements of the density matrix written in a local basis or basis that you are interested in. So very simple. So this is different from the Rényi entanglement entropy that you normally see everywhere, which is you diagonalize your density matrix, right? And then you take the diagonal elements and then you put again here, right? Actually, you can prove that, you know, if you minimize over all the possible bases, then you will get that entanglement one, which you are familiar with it. Okay, so this. Well, this is going to be, for the problems I'm going to tell you, they are all going to be like extensive, related to the size of the volume of the system. For any alpha. Normally, that's the case. Which is like, for the ground states of most of the short-range systems, the other one, which you actually diagonalize it and calculate it, is that one normally shows the area law, or sometimes the logarithmic behavior. But this one is normally just depends on the size of the system. Okay, so, well, of course, so we have both, so we have both, this is the Rényi and this is just the Shannon. So in my word, the von Neumann entropy is just the minimization of the Shannon entropy over all the bases. Okay, so why this is interesting is that because, you know, when you calculate this for the ground states of many quantum systems, especially 1D systems, you get this extensive part, and then you get a constant here, which is shown that numerically that it looks like a universal constant, which I will talk about a particular example of the Ising later, but it has been studied numerically for many spin chains a long time ago. This is a very old story now. You can actually do the same thing instead of the full system. You can also divide the system to two parts, A and B, A and A bar, and then calculate the marginal probabilities for part A, and then put it again in that equation of the Rényi and Shannon entropy. You can do the same thing. Well, something interesting happens. Now, if you are at the critical point, for example, you have the extensive part, and then you have an extra logarithmic part. Now, this extra logarithmic part, it has a coefficient, which for alpha bigger than 1, and in some cases even for alpha equal 1, it looks like it's a central charge. So now, if you do this in normal, the quantity that you know, which is the entanglement one, then we don't normally have this part. So this part is 0, and then what we have here is something like C over something, which is the central charge. Okay, but in this case that I'm talking about, we have this part, and then there's the extra part here, which is proportional to the central charge, and that's a numerical calculation. Okay. So this is for the critical ground states. Yeah, so these are critical ground states. So we have a long range, you know, if you look to the local quantities, you see long range correlations, right? Well, in the case of entanglement, we have the logarithmically growing entanglement. Okay. So Any further questions? Yes, please. Yes, alpha goes to 1 is the Shannon entropy. Okay. So, what? I should go back. Okay, here or more? Okay. So if alpha goes to 1, you need to look at in the limit. So, you know, the 0 over 0, and then when you do this, yeah. The sum of P goes to 1, okay. So, more questions? Okay, so, yeah, so there were all of these studies are more or less, you know, numerical studies. So unlike the case of the von Neumann entropy, which we can really analytically calculate and CFT the entanglement entropy, in this case, so far we don't know how to do it. Although when alpha really goes to infinity, there is a way to handle the things, but let me work on some finite alpha at this moment, okay? Yeah, these are all quantum systems, but you can define this for anything. You can take the classical one too. I mean, it doesn't matter. It's just a bunch of probabilities, right? But in this particular case, I'm just taking a ground state of some quantum chain, or it doesn't need to be even chain. It can be two-dimensional, three-dimensional, whatever. It's written in a local basis. I prefer to be local basis because then it's just easier to think about it, right? So.
There's no entanglement in the classical system, right? There's something analogous?
Well, in that case, when you, for example, this one has a simple interpretation also in the classical one, right? So, for example, if I take for example, 1D transverse field Ising chain quantum chain, and then if I calculate the Shannon, then this Shannon is going to be related to, for example, also the Shannon of one line on the 2D classical one. So it's kind of the relations is much more obvious. But now if you, for example, in the von Neumann entropy or Rényi entanglement entropy, you actually need to there to think about bunch of, you know, Riemann surfaces, like the classical systems, Riemann surfaces that they are glued in a particular way. So even there we have this classical picture, right? So, but in this case it's even simpler. It's even simpler.
How is it simpler?
Well, it's simpler in the sense that we really don't have a bunch of Riemann surfaces glued to each other in a particular way and those kind of things. It's just you take two-dimensional system and then you just look, for example, on a line, you know, your, for example, classical spins are up or down, and you take all these possibilities, configurations, you plug them into this equation of the Rényi and Shannon, and then you see what comes out of it, right? From this perspective, easier, but surprisingly harder to calculate than the other one. Okay. So, more questions? Okay, so, well, so this is something that numerically we knew for a long time, and then somehow recently my colleague Sona Najafi, who is in Watson Center in IBM, she started playing with this superconducting quantum processors, and then they were able to actually make a ground state of a critical Ising chain with 12 sites. And then they were able to estimate the central charge for the Ising, transverse Ising chain and XXZ chain using the same quantities. So you basically, they just prepare it. Well, the ground state of the critical one, which is the hardest part, is just that the ground state should be the critical one. Yeah, so this is something that, you know, they were able to do, and I was able to just help them in theoretical aspect. Oh, well, for the Ising and XXZ, we know Ising is 1/2, XXZ is 1.
So just compare with the...
Yeah, so it's kind of, you know, it's a test. So their machine is working. You know, there is always this debate that, you know. So yeah, well, not 1, 1, but yeah, plus or minus something. Yeah, that's what's right. Okay, so yeah, regarding this part, I think she's the best person to talk about it. As I said, I'm just a catalyst for some analytical part of this story. Okay, so now let me tell you a bit about transfer field Ising change. So I told you the general stuff, right? So that these quantities are interesting. Now I just want to give you an example of the probably everybody is familiar with it. And then I will come back to my original problem, okay? So the transfer field Ising chain is the simplest chain that we have, quantum chain that we have. This is sigma x, sigma, and this is a sigma z. We have a critical point at h equal 1. We have a paramagnetic for h bigger than 1. And for smaller than 1, we have a ferromagnetic one, okay? So if you look, for example, at a quantity like this Rényi entropy that I told you, you will see in the, now I need to fix the basis, right? So here I'm talking about the sigma z basis, but you can do the same thing with the sigma x basis. So what you will see is something like this. The Rényi entropy will have some singularity. The derivative will show some singularity around 1. So if you wish, you could say that, you know, with this quantity, you can detect the phase transition and stuff, but maybe it's not a big deal for some people because there are now at least 100 ways of determining the critical point or phase transition. But this one, I like it just because, well, I can even speak about it for the second year student of undergraduate student. Okay, so you can see, we can see such kind of things for the Ising chain. And then because of Kramers-Vannier duality, since some people, they like to work with the x, mostly for this model, because the x is the order parameter, you can do similar things. It's just there's a Kramers-Vannier duality, so the Rényi entropy in one can be related to the Rényi entropy in the other case, okay? And in this case, if you remember, there was this constant term. You can see that there is a region which is B1x, for example, here, if you take alpha equal 1, you can take different alphas, but here I'm talking about alpha equal 1. So here, the B1x is 0, that constant. You know, there was this expensive part and the constant part. But at exactly critical point, it's a 0.2544. This is a numerical result. So if you take, I think this is the calculation of 2000, numerical calculation of 2010. So the authors, they took like 44 sites, and then they counted all the 2 power 44 sites probabilities. They calculated them, and then they put it there, and they got this answer. And there is a belief that this might be somewhere sitting in the conformal field theory of Ising, but it's an open problem. We don't know what is this problem. It looks like universal in the sense that take a transverse field Ising chain, or if you take, for example, 2-dimensional classical Ising chain on a square lattice or triangular lattice, you get always the same number. So this looks like a universal thing in this sense, right? But we don't know what it is and how to calculate. Okay, yeah. What? So h bigger than 1, it's 0. And h is smaller than 1, it's just a log of 2. So this is exactly at the critical point.
So you claim that this is a jump between one point?
Yeah, so there are just 3 discrete values. So you have the log of 2 and then 1 point and another. Well, it happens. It happens, especially here. This kind of stuff, we have these things. Yeah.
Another parameter you can guess such that 0.254 has a range.
Has a range, for example, something like by changing, for example, alpha. Still, it shows some discontinuity.
I guess I'm asking. It looks like there's a bigger phase space. You claim it's just a single point.
It's a single point. Well, yeah. So the phase transition in the Ising chain is considered the second order. It's a second order phase transition. Here, just we are calculating a different quantity than what people normally calculate. So normally people they calculate local quantities. So this is a kind of a global one because you take the probabilities for the whole system, right? And then you just put them in the definition of Rényi and Shannon entropy. So it's kind of it's just a different quantity, but the phase in the classification of phase transitions, we know that for the Ising transverse field Ising chain, the transition is a second order. Yeah.
But I think there's an inconsistency just with physics. I mean, if you approach one, it can't be just at one, right? There's no experiment that is exactly at one, right? It has to be 1 point something, the experiment.
You are talking about
oh
no, this is a numeric that some people encapsulated 10 years ago, well, in 2010, and this was their conclusion after looking all this how do you say finite size scaling and increasing the sizes and all these things. Okay, so I'm just reporting their.
But there's no experimental way to verify this.
Well, okay. So what's the problem with this experiment? I just showed you that we can have in the IBM's superconducting qubits a periodic Ising chain.
Yes.
But the point is, it's easy to get, for example, h equal 2 or 1/2 or something. Right. When you get close to h equal 1, it's just too much problem, right?
Okay, I understand. The system blows up. Okay,
yeah.
Thanks.
Okay, so any more questions? Well, I hope that at some point they do it because I would be more than happy. So, yeah. So you can also change the alpha, right? And see how that constant changes, and that numerical results that I told you, which was around either 40 or 44, something like that, it's still impressive because you really need to calculate 2 power 40, 44 probabilities, and you actually need to have them in a very precise value. So you can't also just truncate your numbers. If you do truncate your numbers in a non-careful way, you will get really bad results. Anyway, so this is the picture that people they think that this is valid numerically. And for example, alpha bigger than 1, it looks like it's a log of 2. For alpha smaller than 1, it's 0. For alpha equal 1, I just wrote you it's a number we don't know. Okay, so in 2016, we kind of realized that the calculation of Rényi entropy in this model is actually this SPPM problem, which is the sum of powers of principal minors. So somewhere there is a matrix that you need to calculate all the principal minors. Each principal minor is some sort of a probability, right? And then you sum over all of them. Well, this is a sign that probably calculating this quantity is an NP-hard problem because, as I told you, this SPPM problem in general is an NP-hard problem. It is true that for alpha equal 1/2, one can do something. You can calculate it exactly, but for other alphas, well, it's just there's no way to do it. That's the reason that people they were always just doing numerical calculation. Okay. We also realized that the partition function of the Hubbard models is also SPPM. You can do this mapping of the partition function to this problem. And then there are certain problems in machine learning, which is it's called determinant point processes. They are also kind of related to this sum of powers of principal minors of matrices. So these are the reasons that I started getting interested into this problem of estimating the sum of principal minors of matrices. Okay, are there questions? So this is what part was just the motivation part.
Sorry, would you just mind expanding a bit more on the machine learning kind of
so
problems?
Actually, this determinant point process is exactly you take a matrix and then you take the principal minors. But normally when they start introducing it, they introduce it as a marginal probabilities, and their interest normally comes from diversification. Somehow this has some sort of a fermionic nature inside, And so it's kind of, repulsion, right? So for example, they say, this is what they say, that when they want to, for example, you are doing some shopping, right? So they want to kind of give you more variety of the things, so they don't want to repeatedly giving you the same things. So this fermionic nature of this process actually kind of take care of it in a very elegant mathematical way. So that's what
Thanks.
the reason they are interested. More questions? Okay, so let's go ahead. So this is the main result. So one can show that the sum of principal minors of a matrices, power n, can be represented with respect to some Grassmann integrals in this format. Okay, so you can show this by directly expanding this part of this weight, and then seeing that term by term, each one of them are going to be principal minors power n. Of course, here I'm really working with the integer n, so I have no idea what to do with the non-integer real ones. But for the integer n, what I need is basically I need n copies of my matrix, all right? So they are sitting just here, and then they are coupled with these interactions in a particular way here. And then, as I said, you just need to expand this, and then you see that you use this, the rules of Grassmann integration, and then you see that this is actually correct for any matrices. Okay? Well, I don't know that how many people are familiar with the Grassmann integrations, but it's a wonderful thing. I love it. And if you haven't heard about it, just take a look. This is pretty nice stuff. Okay, so let me give you an example. So if n is equal to 1, then that interaction, that coupling part is just like this. And this is like a simple integration. It's, everybody knows it. And this is the determinant of I plus a. Now, if I have n equal to 2, then I can rewrite that things that I wrote for you like this. So I have one copy of these Grassmann variables here, another one here, and they are coupled like this. Okay, some people might see some similarities now with the Hubbard model when you write it in a coherent, fermionic coherent basis, okay? And this is actually a way that we show that also the partition function of Hubbard model is actually the SPPM problem with n equal to 2. Okay, so this one can use to do many things. This is a starting point for doing different kind of estimations. One can also use, for example, Hubbard-Stratonovich to write bosonized versions of this integral, and then try to calculate, to estimate the quantity. We do all sorts of these things, and then I will present you here the simplest things one can do. It's again undergraduate kind of calculation. But before that, let me tell you that this representation that I told you shows remarkable, simple, a lot of symmetries. It shows the UN symmetry and some of the subgroup of UN symmetry, like UN1 symmetry. It shows chiral symmetry, axial U1 symmetry, all sorts of sectorial parity symmetry, symmetric groups Sn. So our particle hole and chiral particle hole, if you have a symmetric or anti-symmetric matrices, depending on for the general ones, we have a lot of symmetries. But for symmetric and anti-symmetric matrices, we have even further symmetries. So another symmetry is just that this sum is actually the same for matrix A, and any matrix AD, which is made out of a diagonal matrix D, like this. So this is also one of the symmetries of the system. So there are a lot of symmetries here, and you will see why I talk about this, because just, being spoiled with the theoretical physics way of thinking about the stuff, so we just thought that it's nice to see what kind of symmetries we can see here. So here there is a schematic of what these symmetries they do. For example, this is for general matrices. So if, for example, UN does this kind of stuff. For example, 1, it forces this kind of relations for the correlations of chi bar and chi. For example, let's say for the SUN2 for symmetric matrices, it forces, for example, VI, which is this one. So you can make your table of each symmetry is doing what for different kind of stuff. And see that later which ones are going to be broken, right? Oh, any questions? Okay. So this is the easy thing one can do. For example, we can try to just write this chi bar and do some the simplest kind of mean field theory that one might think. So writing this for n equal 2, now I'm talking about. So for n equal 2, I can just replace this guy with these values, right? This is what we do normally in the mean field theory. And then this quantity, one can think about like, you know, controlling the extra fluctuations that we have. Okay. Well, as I told you before, there are plenty of ways to do this calculation, but now I'm just talking about the simplest version of it. So after doing that, you know, we get rid of the coupled part of the Grassmann variables. Then now we have just quadratic parts. We can do this integration. It's easy. And then I end up to this estimation for example, for the n equal to 2. Of course, I will have some consistency relations. These are the consistency relations. When I talk about AS, I mean here the symmetric part of the matrix A, and when I talk about the A, I mean the anti-symmetric part of the matrix A. Okay. So, well, this is easy. Now, what happens is that depending on what values we get for the deltas, we kind of break different kind of symmetries. If all of them are 0, we have all this bunch of symmetries. And if some of them are broken, then some of these guys are, when some of them are non-zero, some of these symmetries are broken. Well, in the case of the Ising chain that I talked about, the case that happens is this one, which in that we actually break everything except the axial U1. I don't know why the axial U1 survives, but this is what it is, okay? So this is actually, this table is for the anti-symmetric matrices, because in the case of the Ising chain, the matrix that I have ends up to be an anti-symmetric matrix. Okay. Any question? Okay. Up. Well, it's dead. Up. No. Well, maybe I should do it here. No. We need help. It's working? Oh, okay.
Maybe you can switch from here. Yeah.
Okay.
Maybe it's
Okay.
easier just switch here. It's not, if it's not.
This is this one, right?
Yeah.
Well, it just
right
didn't
left.
work before, okay.
Yeah.
So I need to go ahead. I need to, okay. I talked about this. I talked about this. Again, he doesn't like this slide. I don't know. Maybe there is a mistake. I don't know. Still, it's something is okay. Maybe this one. Is it this one? If I
think it's 26 is kind of blocking some because it might
what
be
was
a
it?
heavy one.
26? Was it the one before was 26?
Yeah. So
Oh,
now
so this is 27? Okay. No, I think there is another one. It's just missing. It's missing one. Maybe you need to open it again one more time. I don't know.
Yeah, but if I close, I don't know how to. Let me call for the guy.
Okay. So if you have any question, we have plenty of time now. SAP. Yes. Eu acho que tem problema com página 20, 26. This, okay. This one, okay. Ok, obrigado.
Talvez é mais fácil você passar só pela direita e esquerda.
Esse aqui, não?
Yeah, it's right and left. I think it maybe be easier than
Okay. So we're back. For the example of the transfer Ising chain, what happens is that if you look to those consistency equations, they end up to have solutions just for the complex deltas. So we have the delta real. These are the real and imaginary parts. And then another interesting thing that happens is that when the size grows, the part that actually this delta ends up to be non-zero is the approach to h equal 1, which was the critical point of the Ising one. So h bigger than 1, the only solution is delta equals 0. When h is smaller than 1, we start having a solution, but those solutions are actually complex solutions. Well, of course, one can play with these deltas and these hyperscaling relations, the kind of things that you do in your statistical mechanics course. But here, I'm interested on the quantity of Rényi equal to R2, right? So these are a bunch of examples of the results for the mean field and the exact numerics. But let me come, well, so these are the mean field, right? So, but for the size L100, as I said, if you do the numerics, the best you can do is around 40, 44, or 45. I mean, that's the order you can do. But here, you can go as much as, well, when I say as much as you want, it's more or less like if you want, you can go even to 1,000, right? Now, well, here, for example, this is the coefficient of the extensive part, and this is that constant. So at h equal 1, we get with the precision of less than 1 the result which is coming from the numerics. And here, I'm showing you this alpha 2 for the exact numeric, which is done for a size up to 20 something. And the other one, when I write this best U, is I mean that if you do this mean field the way that I just showed you, you will get something like this. But you can do much better because there are there are some dualities relations that gives you some extra parameters that you can use them to get a better calculation. So our results for alpha 2 is actually almost on top of the exact results, and these are coming from sizes of order 100. You can do these mean field calculations. So it looks like, even a simple mean field kind of calculation gives you a result that you desire. Of course, you can ask questions like how stable these are. These are the things that one can answer them much easier when you do the bosonize, the equation that I wrote for you. After bosonization, you can do some sort of a saddle point approximation and see how much stable your answer is. And that also gives you some sort of a criterion that, like how much you can rely on the approximation that you are doing. Okay? Any question? Okay. So this is basically the main part of the things that I wanted to tell you. So as I told you before, in the ferromagnetic regime, all the symmetries, in the Ising case, all the symmetries except the axial U1 symmetry is broken in this model. Well, in the negative transverse magnetic field, so you can even go to the negative one, there are some dualities we can use, some fermionic dualities we can use to get a good results for this mean field calculation that I showed you. Then one can play with this like what we normally do in statistical mechanics. Take these deltas like order parameter, or you can also calculate the two-point functions of the Grassmann variables and try to see what comes out of it. But they are not necessarily going to be relevant to the original motivation, but it might be interesting for its own sake. So, well, of course, people, they say that mean field theory for 1D Ising doesn't work. Well, it doesn't work, of course, but here I have a different quantity, and when I write it this way, it works. So maybe nothing surprising. It just depends on what quantity you take for the transfer to Ising. Okay, so we kind of did similar calculations to just see that, this kind of mesh technology is working for other kind of matrices too. For example, we worked on the Laplacian kind of matrices. So you have just a simple one-dimensional graph, imagine, right? And then you may say, well, then you can define the Laplacian on it, discrete Laplacian. This might look like ridiculously simple things, and one should be able to really calculate this easily, but it ends up to be not as simple as it looks like. So when we do the exact the calculation of this, and when we check it with our mean field results, we get quite a remarkable agreement. So in this case, we have symmetric matrices. Well, now we are thinking that maybe this problem is interesting for its own sake as a statistical mechanical model, because principal minors of the Laplacian, they are related to something which in graph theory they call them rooted spanning trees. So this quantity that I wrote you can think about it like a weighted rooted spanning trees, and then you can calculate the partition functions and see that what kind of phase transitions you have. So in this mindset, the n that I introduced is like it can be interpreted as a temperature. Okay. So there are also, you can use the same kind of representation that I told you to find also all sorts of representations that they are more useful for numerical evaluations. Like if you, instead of continuous Hubbard-Stratonovich, if you use a discrete Hubbard-Stratonovich, then you will get a result which is more suited for Monte Carlo kind of estimation of these quantities. So you can develop all sorts of different forms, which, depending on the problem that you are studying, one of them might be more useful than the others. Yeah, so, well, there are other ways also to attack this problem for particular matrices that we call them the diagonally dominant matrices. So when the matrix is a diagonally dominant, there are other representations that one can make and use some sort of estimations. It's quite common for those that they do optimization kind of things. I don't know, you heard about belief propagation or cavity methods, that kind of things. It is possible to get exact from the perspective of a theoretical physicist, not a mathematician, estimates for the matrices that they are actually diagonally dominant. But for this, one needs to think from different perspective. But I didn't talk about that part of the story here. Okay, so conclusions. So my conclusion is that SPPM, I showed you 3 examples that the sum of powers of principal minors appears. One was the Rényi entropy in quantum spin chains. The other one was well, I don't know how much it will be useful for the problem of Hubbard model, but the partition function of the Hubbard model is actually SPPM problem, and also certain problems in machine learning. Then, so this problem has a Bérzin-Grassmann integral representation, which one can use to do a bunch of different kind of approximations and estimation of this problem. Yeah, so the mean field, I just showed you one example of the mean field calculation, which was working pretty well to calculate the Rényi entropy of the ground state of the transverse field Ising chain. Well, of course, there are a lot of questions like, is it possible to use this machinery to, for example, go to n equal 1, which was the Shannon entropy? That's probably the biggest challenge, because numerically, we are convinced that, at least the community is convinced that there is a discontinuity at n equal 1. So the replica kind of mindset is not going to work, at least not with just calculating for integer n and then trying to go for n equal 1. It's not going to work. Maybe one can just massage the way that we do replica in a way that, you know, that particular parameter has some sort of analytical continuation. But in this problem, we don't have this. We have this when you calculate the Rényi entanglement entropy, the one which you diagonalize the reduced density matrix, and right? In that case, in the conformal field theory and almost all of the quantum spin chains shown that, you know, the analytical continuation works. But in this case, numerics shows that, you know, especially for Ising chain, there is a discontinuity at n equal 1. But for the XXZ, for example, those that we have a U1 symmetry, this discontinuity, it doesn't happen at n equal 1, it happens somewhere else. Anyway, it's a challenge. I don't know how we can calculate. Okay, thanks. If there are questions, please.
So thank you, Ali, for the nice colloquium. We have time now for questions.
About the Bérzin-Grassmann integral representation, is there a way to interpret these fermions as something physical? I mean, can you just put them in the model and it somehow pops out, this functional integral over the chi's, or not?
Well, here it's just mostly, you mean, for example, if the correlations or something, they have some sort of interpretation in the other, the physical. I
just mean, so Ising chain is some, I mean, it's some Hamiltonian, but you don't really know what the degrees of freedom are. You know, you have spin, but it's some abstract notion of spin, right?
Yeah.
So since you naturally have these fermionic variables, I'm just thinking that they might somehow have some also abstract.
Yeah, so what happens is that, well, I didn't show this part. So you start with the transverse Ising chain, you do the Jordan-Wigner transformation, you fermionize it. So in the fermionic version, somehow what happens is that, well, if you have a fermion or you don't have a fermion, it means you have a spin up or down for the sigma z, right? So here, the interpretation is like when you do the integration over a particular Grassmann variable, that means that you actually have a one fermion there. And if you don't, that means that, you know, it was like a principal minor, right? I was removing some stuff and keeping some stuff. So the keeping one part was that I had fermions, which meant like I have a bunch of spins up or, you know, okay.
Okay, thanks.
More questions?
Just very generally. So you show that the partition function of the Hubbard model can be mapped somehow in this minor problem, minor calculation problem, no? So this SPPM. Can you show somehow with that the solving the partition function of the Hubbard model is NP-hard? So
no,
can you do
see,
this kind of mapping?
Yeah, so you know, that's what we don't like about this complexity theory people, right?
Okay.
As a theoretician, a theoretical physicist, you know, when somebody says that, oh, we can't solve something, we just don't like it. And the reason is that, you know, they are thinking about, you know, some generic typical matrix, right? So it might not have a solution, but as I showed you, for example, the simple example of discrete Laplace, you can really calculate it exactly. Now, one reason in that case is that the matrix that we have is a kind of a band matrix. So if you have a band matrix, there is always this, this intuition that you probably can solve it exactly. Okay. Now, in the case of the Hubbard model, right, so the matrix ends up to have a structure form if you take one-dimensional case. Now, probably what you have in your mind is a two-dimensional case in which, you know, the matrix is not necessarily a nice form, but it's at the same time, you cannot say that since, you know, the typical SPPM problem is NP, this is going to be also NP. So okay. I don't know. This answers your question.
It would be really nice to prove that. The
well, actually,
model
I wouldn't
NP-hard,
be. I wouldn't mind even if they proved it.
Sorry, I may have lost something, and then the question may be silly. But you've been talking about a chain while in your graphs you had a ring.
I have a
ring. I mean, periodic boundary
yes.
conditions. So the point is, the chain is soluble. The ring is not, because you lack one equation. So then I mean, what I'm trying to say is, you've been talking about the chain all the time, or
well,
yeah, because you see a ring
okay.
one of these circular matrices
okay.
as a solution.
Okay, so in the case of the Ising chain, it doesn't matter that you have something with a boundary, like just a chain, or it's a periodic or open, it doesn't matter. You can find that matrix, which you need to find its principal minors and sum over the powers. In both cases, you can do this. But here, I mostly did it for the periodic one to just for simplification, right? Because then I have a translation on invariancy and makes my life much easier. But in principle, you can do the same thing. But if I wanted to look to the central chart, which I didn't, right? Here I was mostly working with the Rényi entropy of the full system. But if I wanted the central chart, I needed to look to the Rényi entropy of the subsystem. So in that case, I need to work with the periodic one because when I have, for example, if I have a finite size, and then if I look, for example, to the Rényi entropy of a part of the system, if the system is not large enough, then these boundary conditions, they change the coefficients of the look. And it's not anymore just proportional to the central charge. Now, well, if I have really big one, of course it doesn't affect, but if I don't want any kind of, you know, boundary effects, then I prefer to be on a periodic chain. I don't know if this answers, yeah.
Further questions?
So you mentioned a couple times bosonization.
Yeah.
Is this the same bosonization as, like, for example, in a Luttinger liquid?
No, 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 no. It's just, you know, I'm using just a fancy name here. So it's just really, we had this couplings for n equal to, let's say, I had the 4 Grassmann variables, right? We can use a simple, how about the Stratonovich, but continuous one. And then I can change that to just a normal kind of integration. And then now, since I have just a quadratic Grassmann, I can do the integration. Then I end up to have some determinant with just a normal kind of integration. That's what I mean with bosonization. And when you have such kind of things, then you can use all these machineries of the how do you say, saddle point approximation, or some more advanced versions of saddle point approximation stuff. And actually, that one is much better than this one, because there you can also have some control on how much stable is your Mie field. But for just simplicity, I just talked about the fermionic one. Yeah.
More questions?
Okay.
Okay, so if there is no more questions, let's thank again for Ali for the nice presentation.
Okay.
And we have the free afternoon.